Okay, welcome back everyone. In this video, we're going to be looking at how magnetic fields exert forces on current carrying wires and how they can also create torques on loops of wire, which is the basis of many motors. Okay, so this is the equation for the magnetic force on a current carrying wire. And so of course F is force. L is actually the length of the wire, but it's acting as a vector in this case because it's incorporating the current direction. B is the magnetic field in Teslas. And so going back to our first right-hand rule, remember that our thumb will be representing the force. Our pointer finger will be the direction of the current, and the direction that our palm or the curl of our other fingers is going to represent the magnetic field. So don't forget about that first right-hand rule. But let's take a second and try to understand where this expression comes from. Well, we know that this is equivalent to ILB sine theta. And we also know that another equation for the magnetic force is QVB sine theta from a previous part of this lecture. So we can recognize that velocity is really distance over time. And so the sine theta is in place. We don't really need to worry about that. But then if I move the t so that it's underneath the charge there, you might recognize that charge over time is current. And instead of x for distance, we use L. And there it is, ILB sine theta. So it's the exact same expression, if I can get my stylus to work. Okay, so let's see an example of this. So now we have a wire that carries a current of 2.4 amps through a uniform magnetic field of 1.6 Tesla. And we're going to assume that the current is moving in the plus x direction. So we're going to have y this way, x this way, and then into and out of the page is going to be the z direction. So z is actually coming out. All right. So the current is 2.40 amps. The field is 1.6 Tesla in the k-hat direction. And technically that's in the I-hat direction. And this is why engineers sometimes use J for current, because when you have I-hat and then I for current, it can get a little bit confusing. All right, so what's the k-hat direction for this field? Well, it's coming out of the page. So we don't have to draw a lot of them, but just enough to get us thinking about it. So that's the direction of B coming out of the page. And we also are given that L is 0.75 meters. Technically, we should say L is equal to 0.75 meters I-hat and take the I-hat off of the current, because F is equal to IL cross B. So L and B are at 90 degrees, so it's just going to be ILB as the magnitude. And so we can plug that in, and we can obtain for this a force value of about 2.88 newtons. Okay, but what direction is it going? So what you want to do is set down your pencil for a second if you're taking notes. Take your right hand, or hold on to your pencil if you're a lefty, but take the pointer finger of your right hand and point it in the direction of the current. That's also the direction of L. Then rotate your hand. For me, I have to flip my hand over so that my palm is facing at me, so that the magnetic field is coming out of the page. Then my thumb, which is pointing down, is going to be the direction of the magnetic force. And so for me, it's going this way. So this is in the negative j hat direction. And that's it. So now let's do another example. We're going to find how much current must be flowing through a horizontal wire to suspend it in a magnetic field. I should say to be suspended. Okay. If the wire has a mass of 0.2 kilograms. So here's a picture of the situation, and this is going to be a top-down picture. Okay. And we're also told that the current is flowing north. So let's just make it similar to our other diagram. Okay, so we're going to have north going that way, which means compass rose, west is that way, and then coming out of the page is actually up. Okay, so then what we know here is that the force of gravity is actually down into the page. I didn't want to draw it on the wire because that would be a little bit confusing to see, which means that the magnetic force has to be coming up out of the page in order for those to cancel each other out, because we want to suspend it so that the gravitational force is equal to the magnetic force. Gravitational force is just the weight, mg, and this is just going to be ILB. So this means that the current is going to be mg over lb, and when I did my calculations, I just used g as 10 just to simplify things a little bit, and I got 0.02 amps. So you can plug in all the numbers. It would be 0.2 and 10 over 20 times 5. And I'm being really bad with units, but I guess that would be 0.2 kilograms, 10 meters per second squared, 20 meters, and 5 Teslas. And if you're not in base SI units, you got to convert, otherwise you're not going to get a correct answer. So then it says, if the current is flowing north, what direction must the magnetic field be? So this means that L is going that way, and we know that the force is up out of the page. So this means that we need to point our fingers to the right on our right hand, and we also need to rotate our hand until our thumb is pointing up. Okay, so, we want to rotate until our thumb is pointing out of the page. So our fingers are pointing to the right and our thumb is pointing out of the page. Your palm should be facing up like this. Okay, so that has to be the direction of the magnetic field, and so it has to be west. So once again, your finger of your right hand goes in the direction of L. Your thumb has to be pointing out of the page, and your palm has to be pointing up. Okay, so if you take a wire and you bend it into a loop, then you're going to get forces whenever the current is perpendicular to the field, so that you have IL cross B. And if you have current in a loop, on one side of the loop it'll be going one way, the other side will be going the other, so we're actually going to create a torque. All right, so let's think about this. Remember that F is IL cross B. Okay, so that means that on the top of this loop, I and B are actually parallel. Okay, so when L is parallel to B, that means that F is 0. So F is 0 here on the top, and F is also 0 here on the bottom. Well, what about the two sides? Okay, well, I have a wire of length B. Okay, I have a magnetic field of strength B, and I have a current of I. So that means that the magnitude of the force is going to be ILB, but the length is little b. Okay, now what's the direction of that force? Well, we use the right-hand rule, and so now I'm looking at the left side of the wire. So I'm looking at this guy right here. Okay, so this side. Take your finger and point it upwards, and then take your palm and rotate your hand so that your palm is facing to the right, and you should notice that your thumb is pointing into the page. Okay, so that means that the force on, whoops, too far. That means that the force is going into the page. But on the right side, it's the opposite. You point your finger downward, your palm faces into the board or into the page, and you point your fingers downward and you point your palm so it's facing to the right, and then your thumb is coming out of the page like so. Okay, and this is the force. So remember that this is a force and this is a force. Now if I draw a dotted line here, that's like an axis of rotation, then imagine that you just have a rod. Okay, so here's a rod that has a force that's coming out of the page, and we're a distance a/2 away from this axis of rotation. Remember that a torque is R cross F. And R in this case is going to be a/2, and F is going to be I little b big B. And that's going to be the torque for example, the left side. But you're also going to have a torque for the right side of this wire, and the torque for that right side will be exactly the same direction. Okay, it's going to cause this whole thing to rotate kind of like so. It's kind of hard to see that, but the left side will be spinning into the page and the right side will be spinning out at you. And it'll be I, B, B. You add those up and the torque on this wire loop is equal to AB times the current times the field. So that is the total torque. Now in this case, AB right here actually represents the area of this loop. Now that's not always going to be the case, but it is in this example. So let's go ahead and calculate this. We want to calculate the torque on a 40 centimeter length of wire bent into a square. So that means that A is equal to B is equal to 0.10 meters. We have a current of 20 amps, and we have a magnetic field which is perpendicular to that of 0.520 Tesla. Okay, so basically we're going to apply our equation here, and we're going to have torque is equal to ABIB, and if you calculate everything out, that's going to be about 0.104 Newton meters. So that'll be the magnitude of that torque. And then depending on which way you draw the field, it's either going to rotate one way or the other. Okay, so in the next video, we're going to be talking about what happens if you have a charged particle moving through a uniform magnetic field. So moving away from forces on wires to talking about charged particles themselves.